So, separable differential equations are a specific type of first order differential equations. So, this particular method can only be used for first order differential equations, and oftentimes the differential equation has to be linear. So what does separable mean? Separability means we can separate things and put them in groups. So suppose we have dy for xy. Now that particular equation is separable. The reason being, I could divide both sides by y, and I can multiply by dx on both sides. Now if you look at this, I have the y terms and the x terms separated on either side of the differential equation. So this particular equation ends up being separable. Now, let me take another example. Could this be separable? By the looks of it, it seems like, oh, maybe it is not separable. But if I move the cosine x to the other side, it becomes clear that this particular equation is in fact not separable. Why is that so? Well, there is no way that I can have all the x terms on one side and y terms on the other side. What do I mean by that? So if I multiply by dx on both sides, I end up getting that, and clearly the x terms and the y terms are not separate, they are commingled. But if you look at the original dE, which is what we had over here, and you may say, well, I'll just divide by y on both sides and perhaps it will become separable. If you divide by y on both sides, 1 over y dy over dx plus cosine of x would equal x. And that's not separable either, because we have not separated the x values or the x variables and the y variables individually on either side of the inequality. So that equation is not separable. So if a first order derivative is separable, then there are a few steps that we can take to solve this separable equation. So what are the steps or the method of solution? We separate the derivatives and functions of the dependent and independent variables on either side of the equation. Next step, integrate on both sides. And you solve for y. Of course, there will be a constant of integration, and if it is an initial value problem, we can solve for that constant of integration. So, here is an equation, and we want to determine if this is separable. So, dy over dx is equal to sine of 2x. dy would equal to sine 2x times dx. The y term, the derivative of y, and the function involving x and dx, they are on either side of the equality, so it is separable. So we integrate on both sides. Integral of dy is simply y. Integral of sine 2x is negative cosine 2x divided by 2, and we add a c. That c is the constant of integration, and that is the solution to the given differential equation. Keep in mind, separable equations are the simplest form of first order differential equations, and finding their solution are usually easy. Here is another one. We have dy over dx plus 3xy equals 0. What I'm going to do is I'm going to move the 3xy to the other side. It becomes negative 3xy. Divide by y on both sides. We have negative 3x. I'm going to multiply by dx on both sides. Which should give me dy over y equals negative 3x dx. So I have successfully separated the x and the y variables, and they are on either side of the inequality. So all I have to do now is to integrate, because the equation is separable. The integral of dy divided by y is ln of y, and the integral of x dx is x squared over 2. And this particular solution, if you recall from one of the previous videos, is an implicit solution, because the solution depends on y as a function. But we can make it explicit by taking exponential on both sides. So the exponential and the logarithmic function would get cancelled. So we have the absolute value of y is equal to e raised negative 3x squared over 2. But we all know that the exponential is going to result in only positive values. So I could simply write the solution as e raised negative 3x squared over 2 plus c. Here we have a first-order differential equation involving exponentials, and we'd want to know if the equation is actually separable. By the looks of it, it seems that it is not separable, but if we did some algebra here, I could write e raised x plus 2y as e raised x times e raised 2y. I am going to divide by e raised 2y on both sides. That would give me 1 over e raised 2y dy over dx equals e raised x. I'm going to multiply by dx on both sides. I will get 1 over e raised 2y times dy equals e raised x dx. I'm going to move e raised 2y to the numerator. E raised negative 2y dy is equal to e raised x dx. Integrate on both sides. Which would give me e raised negative 2y over negative 2 equals e raised x. Multiplied by negative 2, I'll end up getting e raised negative 2y equals negative 2 plus e raised x. We could take the natural logarithm here on both sides. The natural logarithm and the exponential will get cancelled, so you have negative 2y equals ln e raised x minus 2. Divide by negative 2, so we have y equals ln e raised x minus 2 divided by 2 plus the constant c. So what about the existence interval for that particular problem? Because it is interesting. Since we have determined the solution to be ln of e raised x minus 2 divided by minus 2 plus c, that particular solution will only exist if the e raised x minus 2 part is greater than 0, because we want to have the natural logarithm to have values greater than 0, because the domain cannot include negative real numbers. So the condition here e raised x minus 2 has to be greater than 0. It can't equal to 0, which would mean e raised x has to be greater than 2. Take ln on both sides. Ln e raised x has to be greater than ln of 2. The ln and the e would get cancelled, so x has to be greater than ln of 2. So the existence interval is ln of 2 all the way up to infinity. Okay. So here we have a differential equation, x squared dy over dx minus y equals 0. Anytime we have a first order differential equation, the first thing to do or ask yourself is whether the differential equation is separable or not. If the differential equation is separable, then we can solve it very easily. So if I rewrite this, I could rewrite it as x squared dy over dx is equal to y. Divide by y on both sides. X squared over y dy over dx is equal to 1. Divide by x squared on both sides. 1 over y dy over dx would equal to 1 over x squared. Multiply by dx, we will get dy over y equals 1 over x squared dx. I could rewrite 1 over x squared as x raised negative 2. Now I can integrate on both sides because I have all the x terms on one side and the y terms on the other side. So integrate on both sides. So the left hand side would be ln of y. The right hand side is simply x raised negative 1 over negative 1. So ln of y would simply equal to negative 1 over x. We can exponentiate on both sides. Which would mean e raised ln absolute of value of y would equal to e raised negative 1 over x. The ln and the e would go away, so y is equal to e raised 1 over x plus c. The absolute value is not necessary here because the exponential function is going to give us a positive number. So you look at a problem like the one that we have here and do not try to FOIL, expand, or any of those. Rather think of it this way. We could write the right hand side that a bit of algebra. Now I am going to divide by y minus 2 whole cube on both sides. Those two would go away, so I would have dy over y minus 2 cubed dx equals 1 over x plus 5 cubed. Multiply by dx on both sides, we have dy over y minus 2 cubed equals dx over x plus 5 cubed. So you may think, oh, how would we integrate this? Well, it is pretty straightforward if we remember integral calculus. So I am going to move y minus 2 whole cubed to the numerator, which would result in y minus 2 raised negative 3 dy. Similar manner, we have x plus 5 raised negative 3 times dx on the right hand side. Now we simply integrate on both sides. And the integration here is done via substitution. So you could set u equals y minus 2, which would imply dy is simply du. You could set v equals x plus 5, which would imply dv is dx. So the integral would reduce to u cubed du, u raised negative 3 du, v raised negative 3 dv, which is u raised negative 2 over negative 2 equals v raised negative 2 over negative 2. Those two would get cancelled, so we would have u raised negative 2 equals v raised negative 2. We put the substitutions back, but before that I'm going to write this 1 over u squared equals 1 over v squared, because 1 over u squared is u raised negative 2, 1 over v squared is v raised negative 2, and that is the same as saying u squared is equal to v squared. Put the substitution back in, y minus 2 squared equals x plus 5 squared plus c. Now this clearly is an implicit solution. Because if you FOIL the left hand side and move things to the right hand side, y squared would end up depending on y. So that would make it an implicit solution. So here is another problem, and this is also separable, even though it looks like that it is not. A bit of algebra is all that is needed here. If you look at the first two terms in the numerator, x is in common. So if I pull that out, I have y plus 3. If you look at the last two terms in the numerator, a negative 1 is in common. If I pull that out, I'd have y plus 3. In the denominator, I have x in common in the first two terms, so that is y minus 2. I have 4 in common in the last two terms. If I pull that out, I'd get y minus 2. So we have a y plus 3 in common. In the numerator, if I pull that out, I'd get x minus 1. Y minus 2 is in common in the denominator. If I pull that out, I would get x plus 4. Now, dy over dx would equal to y plus 3 over y minus 2 times x minus 1 over x plus 4. I'm going to multiply by dx on both sides. And move the y fraction to the other side. We would have y minus 2 over y plus 3 dy equals x minus 1 over x plus 4 dx. And you look at that and say, oh, well, how do we integrate this? It is separable because we've separated the y terms and the x terms here. But how do we integrate? There's an algebraic trick here that we can do. So what I'm going to do is I'm going to add and subtract 3 in the numerator. I'm going to add and subtract 4 in the numerator on the other side also. That would give me y plus 3 minus 5 over y plus 3 dy equals x plus 4 minus 5 divided by x plus 4 dx. I can split the integrals because I have a common denominator, so I'm splitting the numerators. So the left-hand side becomes that, and the right-hand side, in a similar manner, would become so that would get cancelled. So we have integral dy minus integral 5 over y plus 3 dy equals integral dx minus integral 5 over x plus 4 dx. The integral of dy is simply y, and you can use a substitution. Let's just say u is dy plus 3, which would mean du is dy. So the second integral would simply be 5 times du over u. On the right hand side, the integral of dx is just x. And we can use the substitution v equals x plus 4, which would imply dv is dx. So y minus 5, integral of du over u is simply ln of u. Integral of dv over v is ln of v. Plug in the value of u and v back in. And I'm going to move that term to the right hand side to simplify. So y would equal x minus 5 ln x plus 4 plus 5 times ln y plus 3. Should have given more space here. X, I have a 5 in common, so I have 5 times ln of y plus 3 minus ln of x plus 4. And if we use the properties of logarithms, we'd simply write it as ln of y plus 3 over x plus 4, and plus a constant. Again, this is an implicit solution because y depends on a function of y. So here's the differential equation. Note that here x is the independent variable, and what t is the, oh sorry, I have it backwards. X is the dependent variable and y is the independent variable. So we have to group all the x terms and the t terms together. So x times dx over dt would equal to x squared plus 1 squared. Group all x terms on one side, so I'm going to divide by x squared plus 1 squared. Multiply by dt on both sides. And integrate, because I have all x terms on one side, t terms on the other side, so and the left hand side can be integrated with substitution. We could say u is equal to x squared plus 1, which would imply du is 2x dx, which would imply x dx is equal to du over 2. So I'm going to replace x dx on the left hand side of the integral with du over 2. The denominator by u squared. The right hand side would simply be t. I can move the u squared to the numerator and write it as u raised negative 2 du, and that would equal to t. If I integrate u raised negative 2, I will get u raised negative 1 over negative 1. That would equal to t. So u raised negative 1 over negative 2 equals t. U raised negative 1 equals negative 2t. So we are trying to find the solution to x, and our substitution was u is x squared plus 1. So x squared plus 1 raised negative 1 would equal to negative 2t plus the constant of integration. Here we have the value of x when t is pi is 1 over 2. So I'm going to plug in one over 2 squared plus 1 raised negative 1 would equal negative 2 pi plus c. So 1 over 4 plus 1 raised negative 1 equals negative 2 pi plus c. Which is 5 over 4 raised negative 1 equals negative 2 pi plus c. So c would be 4 over 5 plus 2 pi. So what is the explicit solution? The explicit solution is simply x squared plus 1 raised negative 1 equals negative 2t plus 2 pi plus 4 over 5. In other words, we are simply trying to find the solution for c using the condition that's given. By all means, this is simply an initial value problem. So here we have y prime, which is dy over dx equals 2y e raised negative x squared. Divide by 2, well, let's multiply by x on both sides. Then divide by y. Multiply by dx on both sides. Now we have separated the y terms and the x terms. So we integrate on both sides. The right hand side, you can integrate it using substitution. If we use u is equal to x squared, du would simply be 2x dx. So the right hand side would simply become e raised negative u times du. The integral on the left hand side is ln of y. On the right hand side, it's simply e raised negative u over negative 1. We can replace the u with our substitution. And we have c. And when we plug in x to be 1, y of 1 is pi. So the value of y is pi when x is 1. So we have ln of pi equals negative e raised negative 1. And that would be, or plus c. So c is e raised negative 1 plus ln of pi. So the explicit solution here ln of y equals negative e raised negative x squared plus ln of pi plus 1 over e. I'm simply rewriting e raised negative 1 as 1 over e. So we want to find an explicit solution for the initial value problem and identify the existence interval. So the first step is to group all the x and y terms together. So 2y multiplied by 2y on both sides. Now multiply by dx on both sides. We'll get that. We integrate on both sides because we have successfully separated all x terms and all y terms. So integrate on both sides. So the integral here is 2 times y squared over 2. The integral on the right hand side can be computed using substitution. If you integrate it using substitution, you'd end up getting 2x plus 1 squared divided by 2. Now we have the initial condition, so we'll get rid of the 2's. So there is a constant of integration. So when the value of x is negative 2, the value of y is negative 1. So we plug in the condition. So 1 is equal to negative 4 plus 1 squared over 2, which is 9 over 2 plus c. Move the 9 over 2 to the other side, we will get c to be negative 7 over 2. So the solution is y squared equals 2x plus 1 squared over 2 minus 7 over 2. Which would imply, I guess I'll write it over here, y is equal to the square root of that. Now, since we have a square root, the term inside the root has to be greater than 0. So what we require here, I may have to move that problem to the next page. So the condition the term inside the root has to be greater than 0. So if we simplify by multiplying by 2 on both sides, we would have 2x plus 1 squared minus 7 to be greater than 0. So 2x plus 1 squared will be greater than 7. If we take the root on both sides, 2x plus 1 is greater than square root of 7. 2x is greater than square root of 7 minus 1. And x has to be greater than square root of 7 minus 1 over 2. So the existence interval is x greater than square root of 7 minus 1 over 2. But you look at the problem, the value of x is negative. We have y of negative 2 to be equal to negative 1. And you may wonder, well, what happened? Well, the key here is plus or minus. So for the root 7, so we could write it as plus or minus root 7. So plus or minus root 7, because we are taking the square root. So x has to be greater than square root of 7 minus 1 over 2. Or x has to be greater than negative square root of 7 minus 1 over 2. So negative square root of 7 minus 1 over 2 will still not satisfy the problem. So do we have a proper solution to this particular equation? Well, we have an explicit solution, which is what we found. So the solution exists on that, but it will not satisfy y of minus 2 equals minus 1. In other words, it wouldn't satisfy the initial value problem. We were able to find a solution, but unfortunately the existence interval goes against what we need to have in order for a solution to exist. That is, y of minus 2 must equal minus 1. That is a condition that we have for the problem. But minus 2 is actually less than negative square root of 7 minus 1 divided by 2. So minus 2 is not going to fall in that interval. So even though we have an explicit solution, we don't have a solution that would satisfy the initial value problem because of the existence interval. So I am going to move this part to the next page. So that is a first order differential equation in the normal form, and we want to know if this is separable. From the looks of it, it seems like it is. So I'm going to move the negative e raised negative x dy to the other side. Divide by e raised y on both sides. Divide by e raised negative x on both sides. Move the exponents to the numerator. So I have the x values on one side and y values on the other. All we have to do is integrate now. So we integrate on both sides. Integral of e raised x is e raised x. Integral of e raised negative y is e raised negative y over negative 1 plus c. So we have e raised x equals e raised negative y over negative 1 plus c. And when the value of x is 0, y is 1. So e raised 0 is equal to e raised negative 1 over negative 1 plus c. E raised 0 is 1. So 1 would equal to e raised negative 1 over negative 1 plus c. I could rewrite, you could convert it to a decimal, but I'm just going to keep it in terms of e. So if that e raised negative 1 moves to the other side, it becomes positive e raised negative 1, because there is a negative 1 in the denominator. And the value of the constant is c is 1 plus e raised negative 1. So the solution e raised x is equal to e raised negative y plus 1 plus e raised negative 1. This particular equation will satisfy the initial condition. So when we plug in 0, it is going to satisfy the initial condition. I believe I forgot a negative there. Yeah, negative. So you can verify. So when x is 0, we need to have y as 1. So e raised 0 minus e raised negative 1 plus 1 plus e raised negative 1, and we have 1 equals 1. It checks out, it works. So the initial condition is satisfied. And what is the existence interval? If you look at the equation, or the solution without the constant was e raised x equals and we could plug in almost any value for y. So the initial condition is satisfied, but no matter what value of y, x we plug in, it is going to give us a positive value on the right hand side. So e raised 0 is going to be 1, e raised another number would be positive, and on the left hand side we are going to end up having negative e raised negative y. And we will take natural logarithm here, and there is going to be a situation if the constant is not involved, because we have a negative sign. So this entire solution is valid if and only if we have c defined properly. And in this case, the existence interval should work, and it would work provided we go from 0 to infinity. I'll just say where c is equal to 1 plus 1 over e.